In our videos, we've been talking about developing a sampling plan. So the first step was to define the population of interest. What is the group that we ultimately care about getting information about or from? Then we chose a data collection method. Are we doing a survey, a focus group? How are we going to be collecting our information? And within those, we might be then choosing a collection method within that. So from a survey, are we doing executive interviews? Are we sending it out by snail mail? How are we going to be collecting data? And then we identify a sampling frame. So this is going to be a list of people within the population that we could then use to get our sample from. So what are we using to kind of specify here's the group that's in the population that could potentially be in the sample? And then from that, how do we actually get people to be in the sample? So what is our sampling method? And our last videos, we looked at probability sampling methods and non-probability sampling methods. So the next thing we need to do is determine how big of a sample size is appropriate. How many people our participants do we actually need in our research project? So let's look at determining sample size. Now, one thing to consider is that if your budget is not enough to allow for an adequate sample size, then either you need more money, or if that's not possible, then don't do the research. If you cannot get an adequate sample size to inform the decisions that you need to make, then you're better off not doing the research. Now, different types of research have different sample sizes. So if you are doing more exploratory research, you will have a much smaller sample size. We talked about focus groups being 8 to 12 people. Your interviews, you may only interview 10 to 20 people. So there's going to be much smaller when we do exploratory type research. When we are doing quantitative analysis, when we are doing descriptive research methods, when we're looking at doing things like surveys, whether it's cross-sectional or longitudinal surveys, if we want to do statistical analysis to basically say, here's what we found in our sample, and here's what it means about the greater group, the greater population, we're going to need a appropriate or a bigger sample size. So we're doing our calculations here, which get us started into more of that statistical analysis we'll be doing in later videos. But we need to make sure that it is sufficient sample size to be able to detect differences when there really is using our statistical methods. So we need to make sure that our sample size is appropriate for what we want to do with the data. If it is not appropriate for what we want to do with the data, we either need to do something different with the data, so change the type of analysis that we're doing, or not do the research project. Now, when you have an RFP, a request for proposal, the client who's creating that RFP will often put an expected sample size. Or if you are building a proposal as a response to an RFP or for your organization itself, then you may specify what sample size is necessary in order to get the results that would actually inform decisions within the organization. You're basically showing that if you can't get that appropriate sample size, then any conclusions that would be drawn from your work may not be accurate. If you're doing stratified sampling, the larger the number of strata, we talked max 6, but the more strata that you have, the bigger the sample size you will need, because you are going to need enough variety within each group to basically represent the different views and perspectives of people who belong to that particular cohort. So how do we determine sample size? Well, if you have a survey with lots of different questions, then you should do a sample size calculation for a couple of the different questions, and then you go with whichever has the largest sample size necessary in order to complete the entire project. So let's look at how this would work. Now, the questions that are going to require the biggest sample size are going to be the questions that have the most different possible answers. So we would take those particular questions and figure out what the sample size is, and then that becomes the minimum sample size for the entire survey. So let's look at a question where we would want to calculate the average, okay, the mean. So calculating sample size for problems where we would summarize that answer to that question with an average. To figure out the appropriate sample size, we're going to need a couple different things. We are going to need a level of confidence. We're going to need a standard deviation for that variable for the entire population, and we're going to need an acceptable amount to define the acceptable amount of sampling error. That is, how far off are you able to be in that question and still be okay with it. Okay. Now, your sample size is going to be bigger if there is more variety in the responses from that population, and if you're going to have if you're less willing to accept sampling error. Okay, so for example, let's suppose we ask you a question, and here we have an open-ended question that says, how much do you spend when you go on vacation to Vegas? Okay, if the people who go to Vegas spend quite a different amount, so some people go and they only spend a couple $100, some people go and they spend tens, $20,000. That's a lot of different responses, different numbers. Those numbers are quite far apart. $200, $20,000. If there is a lot of difference in the answers, so then what we're going to need is a bigger sample size. Now, if when we try to summarize this information and say the average spent on this Vegas vacation is $1,000, if we're okay with the actual number, so our sample average is 1,000, but in reality, maybe the true population average is 1,500. We're willing to be off by 500. As opposed to we got our sample, the average is 1,000, but we're only willing to be off by 100. So the true population average is 1,100. If you have to be very, very precise, so any decisions your organization makes requires that estimate be very close, that sample average be very close to the population average, you're going to need a bigger sample size. So how precise do you have to be when you are coming up with this number to make a decision for the organization? How much variety is there in the responses? If everyone who goes to Vegas spends between $800 and $1,200, so there's very little difference, then we don't need a big sample size. But if we're looking at the difference between $200 and $20,000, we need a much bigger sample size. And then how confident do we need to be in the results in order to move forward on our decision making, right? So those types of things are going to impact the sample size. So when you are calculating the sample size, the allowable sampling error is going to be set by the researcher in consultation with the client. So ask them, if you find out the answer is this and it's really this, would that change your behavior? So you're trying to figure out how sensitive it needs to be. You're also looking at how confident they need to be in those results. Our level of confidence is going to tie to a Z-score. So a Z-score looks at a standard normal distribution. Here's the average for the population. Here's mu. Okay. Now, how confident do you need to be? So if there is some variability, how far away can you still be? How much error are you willing to put up with? Do you have to be right 99% of the time, 95% of the time, 90% of the time, 68% of the time? So how sensitive in terms of when we go to make a decision based on these responses, how much kind of a safety net buffer is there for that? Okay. And then how much variability is there in that population? So we could use results from prior surveys, from pilots, from secondary data analysis. We could use judgments. All of this can help us inform what that sampling error level of confidence should be. And if we have existing information about the population, how much variability is there in that population. So to help you kind of see how this works, let's look at some examples. Okay, I'm actually going to skip that example and come back. Let's do this one. Okay, Alberta Tourism would like to estimate the average annual expenditures on food and lodging while on fishing trips. Samples from a list of people who purchase fishing license. So we're going to recruit from the list of people who purchase fishing license. And as we get this average annual expenditures, right? So we got to find X bar, and we're going to use X bar to tell us about mu. So we're going to find the average that people spend on fishing trips in our sample, and we want to use that to tell us about the average people spend on fishing trips in the greater population. Now, we want to be within about 25 bucks. So between X bar and mu, we want them to be less than $25 apart. We want to be fairly accurate in this estimate. Okay. Now, one-day trips may cost as little as $0. Overnight trips have costed as much as $750. Okay. So we know from historical data that there's this range, right, between 0 and 750. So we want to use our formula here to estimate the sample size. Well, how do we convert this information into this formula? Well, we start with E, our sampling error, and let's actually just go back up. Remember, here we have E, and E being the acceptable amount of sampling error, X bar minus mu. So in this particular example, our E is going to be 25. That's how far apart they can be. Then we're going to need to find our Z number. Okay, so how confident do we need to be? Well, when it comes to our confidence level, we can be confident that we have the right information 95% of the time, 99% of the time, 68% of the time. The more accurate you need to be, so if we were to take multiple samples, what this is telling us here is that if you recall, when we were looking at sampling error, each time we found an average from a different sample, it was a different distance away from the population mean. So we want to be within that $25. We want to have them close. But if we took lots of different samples, what percentage of the time do we need them to be that close to each other? Is it all the time? Can we go with a lower number? Now, what happens? The higher, the more accurate you need to be, the less willing you are willing to be wrong. So if we need to be 99% confident, it's going to make your sample size much bigger. If you can get away with being right only 95% of the time, so you take these samples give you different averages. If you need them to be within that range of the population average, but only 95% of the time, you're okay with a little bit of error, then your sample size can be smaller. And so if we go to our Z scores here, right 99% of the time is a Z score of 2.58. 95% of the time is a Z score of 1.96. So where this comes from is that if you are within one standard deviation of the population mean, then that is about 68% of this distribution. If you're within two standard deviations of that average, then you are really right around that 95%. If you want to get closer to 3 standard deviations, right, then that's a much higher percentage. So these numbers here, you can take these as they're written to show you where they come from. If we were to look here on a standard normal distribution table, this number in here is the percentage. This is the area to the left of the Z score. So on our image here, if we were looking for this number, it would tell us everything to the left. So if we went to look at, let's go look at 1.96 on the Z. So these are negative. Let's go, this is everything to the left of the Z score. So be careful what kind of Z score table you're using. They sometimes report them differently. But 1.96, okay, what you see with 1.96 is that it is 97.5 here. So what that tells you is that everything to the left, so all of this here and this adds up to 0.975. Well, when we look at these Z scores, what we're caring about here is the middle. So we need to adjust that to be within our range. So we're essentially going to actually take our 0.975 and subtract 0.5 from that, which gives us 0.475. So that would be the portion here. And then if we go the other direction, equal amounts, so we add 0.475 to it, then we get 95%. So a Z score of 1.96 covers the middle 95%, which means then on that outer extremes, that those are the points at which we will be incorrect 5% of the time. But each time we're taking an average, we should be mostly hitting that population average, but there's going to be some variability in that sample average, centering around that population average. And if we want to then make sure that we're close to that population average 95% of the time, then we're going to use a Z score of 1.96. If we want to be more accurate, we're not willing to be wrong. So we need the averages to be close to that population average more often. Then of course you need a bigger sample size for your sample to be more like the population. And so let's say you want to be right 99% of the time, a 99% level of confidence, then you're going to use a Z of 2.58. And the way that you would find that is you can see here at 2.5 and then over to 2.58. You see this number here, 0.99506. That's showing you everything to the left. We would subtract from 0.99506.5 to just get the portion that's to the right of that population mean, and then duplicate it on both sides. You'll see the 2.58. Now, let's see. Can I write on this one? Here we go. 2.58, 0.99506 minus 0.5, right? 2.58, 99506. What do we get? 0.49506. And then you multiply that times 2, so 0.49506 plus 0.49506, 8. And this is what, 98, 99. So you can see how we're getting to 99% at 2.58. So you don't have to do this. We'll get later to Z scores and tables as we get more into stats. But really what you just need to know is Z equals 1 for 68%. Z equals 1.64 for 90%. Z equals 1.96 for 95%. And Z equals 2.58 for 99%. So if you just capture that information, that'll give you what you need to calculate sample size. So in this particular case, the Z we would use if we are wanting to be accurate 95% of the time. So each average, remember, is going to be a little bit above and below the population average, but it needs to be close to that population average 95% of the time. We would use a Z of 1.96. If you need to be 99% confident, then 2.58. Okay, so those are usually the two that you're going to use. You might use 90% if you're willing to have a higher error but that'll give you a lower sample size. You might go with 1.64. So your Zs are going to be 1.64, 1.96, or 2.58 in your sample size calculations are really what you're going to use. 90%, 95%, 99%. Okay. All right. So then the other piece we need here is our sigma squared. And our sigma squared is going to deal with how much variability there is in the data. So remember we talked when we first looked at this that the minimum was 0 and the maximum was 750. You can estimate your sigma by looking at, so sigma is equal to, we can take our maximum here of 750 minus our minimum to get the range. Okay, so our range here between minimum and maximum is 750. And if you divide that by 6, you can estimate sigma. Why 6? Because if we look at this normal distribution that I keep just, coloring all over, if you look at the minimum and the maximum, they should be 3 standard deviations in either direction. So if we can go 3 this way and 3 that way, that's 6. Okay? Which means I can take my maximum, subtract my minimum, get this distance here, and then divide it by 6. That will estimate my standard deviation, our sigma. So 750 minus 0 is 750. 750 divided by 6, we get a sigma of 125. All right. I want to calculate the sample size for this particular question. This particular question is an open-ended question where they write in a number. So because it has the most possible answers, if you have a question like this, this will set the sample size for your entire survey. So we would then take 1.96 and square it times 125 and square it, divided by 25 and square that. Okay, so we do this calculation and we get, see if I can pull up my calculator here. So we get let me just put it up. Will it go? No. Don't know where it is. All right, let's try this. 1.96 times 1.96 is basically 3.8416 times 125 times 125 is 15,625. And then we look at 25 squared, which is 25 times 25. Is 625. Okay, 15,625. 15,625 times 3.8416 divided by 625. You should be getting about 96. My face is covering up most of this crap. All right, equals 96. So in all of this calculation, we found level of confidence, 1.96 is our Z, sampling error, we're willing to be within 25 of the population mean. We estimated our sigma, our standard deviation, that variability within the population by looking at the maximum and the minimum for historical information, dividing by 6. Based on this particular set of information, we would need a sample size that was at least 96 participants. Try doing this calculation again. What happens if instead you make this 2.58, so you need to be more confident, or if instead you needed to be within $10 of the population mean? Notice that when you put any of these numbers in, because you are now squaring bigger numbers on top and squaring smaller numbers on bottom, that your sample size gets bigger. So we need to know this formula here. If you have open-ended questions where they write in a number, that's going to set it for your entire survey. And that's because if instead you have attitude scales, you'll use the same formula, but the level of variability is much lower because it's not every possible number between 0 and 750. It is, let's say you have a 5-point scale. If I have a 5-point scale, then the variability is really only going to be, right? They could have picked 1, strongly disagree, or they could have picked 5, strongly agree. That's how much it's going to vary. And so there, the sigma squared is going to be 1.2 or 2. So let's give this a try. So let's suppose that we have a question. How would you rate, I'm just moving my head down here. How would you rate the quality of service at McDonald's? And we have a 5-point scale between very dissatisfied and very satisfied. So very dissatisfied, somewhat dissatisfied, neither, somewhat satisfied, very satisfied, right? 5-point scale. All right. So in order to do this, we need that same formula that we had before. We need n equals z squared, sigma squared, divided by your sampling error squared. Okay, so we need to make some decisions. Let's start with the level of confidence. So how confident do we have to be? We're going to find the average response to this question in our sample. So we might say the average is somewhat dissatisfied. Next time we do a sample of different people, they might be somewhat satisfied. So we would say, what percentage of the time do we need that average from our sample to be the same as the average from the population? Let's suppose we want to have 99% confidence. Okay, so we're going to use a Z of 2.58. Okay, now we need to determine our E, our sampling error. So how far off are you willing to be? Well, the challenge with the scale is that there are only 5 choices: very dissatisfied, somewhat dissatisfied, neither, somewhat satisfied. So we go back to the question of, if the results were somewhat dissatisfied versus if the results were neither, would those 2 different responses change the decisions your organization made? Well, probably, right? And if the answer was somewhat dissatisfied versus somewhat satisfied, would that change your behavior? Yes. So we probably need a sampling error that's fairly small because we really don't want it to be a different point on the scale when it really is the other point on the scale, because that would actually mean we made the wrong decisions. So maybe our sampling error is only going to be 1. That is, if we're really only willing to be off on the scale between our very dissatisfied, neutral. You're really only willing to be off by 1. And maybe you're not even willing to be off by that. Maybe your sampling error is only a half because you really can't be pushed to the next part on the scale without it substantially changing your behavior. So let's start here. We'll do a 99% confidence, an error of 1. And here then we need our sigma squared, or our sigma. And this is going to give us our sigma squared. And so we have here that we have our sigma squared, and we'll just go with the upper bound here of 2. So then to do our calculation, we would do 2.58 squared times 2, because that's already sigma squared, divided by 1 squared. And so we end up with, right, 2.58 squared times 2, right? And we get a very small sample size, right? It's only 13.3128. And with sample size, always round up because you don't have a third of a person. So this really is a sample size of 14. So notice that if you had only 5-point Likert scale type attitude type questions, even with a 99% confidence, we only really need a sample size of about 14 people. Now, in a sampling error of 1, again, that would push you all the way from here to here. That's probably too big. So let's make that smaller by changing this from 1 to 0.5. And we'll change this to 0.5. Okay. So then we're going to divide our 14 that we just calculated, because that was 1. We're going to divide that by 0.5 squared. Well, what is 0.5 times 0.5? That's 0.25. So we're going to essentially take that 13.3128 divided by 0.25. You'll notice now we get to, instead of 14, now we're looking at a sample size of 53. Okay, so by changing that sampling error to be smaller so we don't quite make it to the next part of the scale, then we have a big increase in the sample size. So if you had only attitude scale questions and you made different decisions based on if it was dissatisfied versus neutral, 99% confident, you'd need 53, actually need 54, because it's 53.2512. So we would, again, my face is covering it. We would need actually 54. Always round up with sample sizes because you can't have 0.2512 of a person. So we would need, that looks like it's 81. That's not 81. That's 54. We need a sample size of 54. So if the survey was only attitude scales, maybe it had a couple more questions that were more dichotomous, yes, no, so those would require a smaller sample size, then we would need at least 54. So we go with whatever question is the most complex in our particular survey. Now, this was the calculation we looked at here when we summarized the data in terms of a mean, an average. We used this formula here. And we can use that formula for our attitude scale questions. We can use that for when they write in a number. What if you have questions where it is summarized based on proportions, on percentages? If we're doing it based on percentages, then we are going to need to use this formula instead. So think about nominal questions where there are categories. We would want to say, 20% fall into this particular category. And if that's true in our sample, is that true in the population? Well, to figure out the sample size for those types of questions, we use this formula here, where our Z is still the same level of confidence. Okay, our E is the acceptable amount of sampling error, and P is an estimate of the population proportion. If you have no idea what the percentage is in the population, then you go with a P of 0.5. That will give you the largest possible sample size given your level of confidence and your sampling error. So it's essentially saying if you don't know anything about the population, let's err on the side of a bigger sample so that it's more likely to represent the population. So let's look at how this works. All right, let's look at an example here. All right, so Alberta Tourism would like to know the percentage of overnight fishing trips that are done by people from out of the province. So we can think of a question basically asking, are you from the province? Are you out of the province? Here we simply have a dichotomous question, in or out. Now we're going to take the list of people who purchased fishing license, and that's going to be our sampling frame, and we'll pull from there a sample. The question is, how many people from that fishing license list do we need to participate in our study? Well, if a study 2 years ago found that 18% of people were from out of the province, then for the P here, we will use 18%. If we didn't have that data, and we'll do a comparison in just a moment, we'll use 0.5. Okay. It's believed that the percentage of out-of-province visitors has increased. Okay, so it might be more than that. And so we're going to take a look here with our study. We would like to be within 2% of the actual percentage. So here we are with our sampling error that we need to be within 0.02. And then it comes down to our Z-score that goes with our level of confidence. That is, if we did a sample and we got a percentage, 18%, 25%, each different sample is going to give us a different proportion of people from out of the province. What percentage of the time, right, do you need that average to be the same as the population? In other words, how confident are we? How much error are we going to allow in our study? So let's suppose we go with a 95% confidence level. So what is the Z-score for a 95% confidence level? It's 1.96. And while we're trying to recall, what if we wanted 99% confidence? Then we would go 2.58. If we were okay with 90%, so we're allowing a bit more error, then we would go with 1.68. So you'll remember 1.64. 1.64, 1.96, 2.58. Those are the keys to remember as we're looking at sample size determination. All right, so let's do this calculation. We have 1.96. Let's just make some space here. 1.96 that we're going to square. We have 0.18 times 1 minus 0.18. So that's those who are from out of province, and then those who are not from out of province, that's the 1 minus 0.18. And then we divide by our the allowable error here, 0.02 squared. All right, so we do that calculation. (1.96 times 1.96). We saw that number before. That was 3.8416. And then we have 1 minus 0.18. Right, so we get this times 0.18 times 0.82. And all of that is going to be divided by 0.02 squared, which 0.02 times 0.02, right, is 0.00004. Okay. All right, so what do we get? 3.8416 times 0.18 times 0.82 gives us 0.567. Divide that by our 0.004, and we're getting our sample size here, 1418. Right, we get 1417.5. Technically, you get 1417.55. Always round up, even if it was 0.00001. Always round up because you can't have a fraction of a participant. And so in this particular case, where we have this question, need a sample size of 1418. And you need a sample size of 1418 because you believe that there's 18% of those, the proportion is about 18%. Notice that if we change this to 0.5, so if we redid this calculation and instead we did 0.5, so it would still be that 3.8416 times, in this case, 0.5 times 0.5. We get 0.9604 divided by 0.004. Notice if you change this from 18% to 50%, you now have a sample size of 2,400. So the sample size is bigger because we don't actually know what percentage was out of province. So we can see here we need a large sample size if we have this type of question in our survey. So what I recommend if you build a survey and you're trying to figure out the sample size is take one of the questions that it's a proportion question where you'd summarize it with a percentage for the groups. If you have an open-ended one where they write in a number, do that. And then do your scale, get your 3 different sample size calculations. Whatever the bigger number is the minimum sample size for your project. Okay. So we could do another example of sample size with proportions. So how big of a sample size would be necessary to determine if 16% of M&Ms are really green? Okay. In order to do this calculation, right, we need some information about, we need our Z-score, we need our error, we need our population proportion. Okay, so we could do our calculation. Let's say that it's a 95% confidence. If we're 95% confidence, what's the score? 1.96. How far off are we willing to be? Well, if we're willing to be off by 2%, then that would be 0.02. If we're only willing to be off by 5%, then that's 0.05. If we have to be 99% confident, then that Z is 2.58. So depending on level of confidence, depending on amount of error, we could do the calculation. And we have historical information from M&M that says that it should be 16%. So you could do this calculation. And so take a moment and try these. So try 95% confidence and 2%. If you do that, you end up with a sample size of about 1291. If you repeat the 95% confident but do it with the 5%, you end up with a sample size of 207. If we're trying to go 99% confident and we're willing to be within 2%, then we get a sample size, we need a 2,237. So we would need to test 2,237 M&Ms, right? To see if it really was 16% green. Oh, you can't even see that because it's hidden below. And if we were willing to have a 5% error, we're willing to be off by 5%, so it could be 16, it could be 21, but we need to be 99% confident. You can see that the sample size is much smaller at 358. So you can see how your choices here in terms of the level of confidence make a difference. So by going from 95% confident to 99, we go from a sample size of 1291 to 2237. I'm trying to find my face so I can move it down here. So it almost doubles, right, as we go from 95% to 99% confident. And when we go from 2% to 5% sampling error, you can see the difference here, right? 1291 versus 207, or 2237 versus 358. So with the proportion, how far away from this 16% are you willing to be, and how confident do you need to be? That's going to impact your sampling size. So you need to be able to make an argument for the confidence level you chose, the sampling error you chose in any of these sample size determinations. All right, one more here, which is what if your population is not very large, so that your sample is more than 5% of your total population. So in that particular case, there's actually an adjustment made to the calculation. We adjust the sample size if your sample is more than 5% of the total population. So in this formula here, we're going to revise the sample size and get this N with a little dash after it. And it's going to be the original sample size, which is the lowercase n, and the population size. So we came up with, in the previous calculation here, let's say with this 358. That 358 was 99% confident and we were allowing an error of, what was that, 0.05. Okay. So if that was the case, that we were sampling 358, and what if the actual population was only 400? So then what we would do is we would take the sample size we calculated was 358, but the population was only 400. So we're going to actually do an adjustment here. And when we do this adjusted calculation, what we end up with is that we don't actually need a sample of 358 if the population is only 400. In fact, we can instead just get a sample size of 190. So the original sample size calculations took into consideration sampling error, variability, confidence, but they didn't take into consideration your sample size compared to the overall population size. So if your sample is more than 5% of the total population after you do these methods, you can do an adjustment to take that into consideration, and it will move your sample size down. So another calculation to do as you're determining the appropriate sample size for your process. So we've defined the population of interest, we've chosen a data collection method, we've identified a sampling frame, selected a sampling method, convenience, snowball, random sample. We've just determined the sample size. Remember that you do it for multiple questions in your survey, and then what you do is go with the bigger number that you calculate. That's going to be the minimum in order to be able to determine the differences you're looking for. Then you're going to develop a sampling process. So the last thing we want to look at here is the sampling plan, and that is the instructions. So if we are doing like a face-to-face survey, so we have to send people out to houses, how do they actually go about collecting, if we're collecting 190 surveys and we are using whatever method we're using for sampling, how do we actually implement it? So in this particular case, we would write out these instructions that would say, okay, in the instructions that follow, reference is made to follow your route around a block. In cities, this will be a city block. In rural areas, this is going to be land surrounded by a road. If you come to a dead end along your route, proceed down the opposite side of the street, traveling in the other direction. Continue making right turns where possible, calling on every third occupied dwelling. So notice in this particular case, it's every third house. So what method is that? Right? Remember, that is our systematic. If we go back. Notice the systematic sampling, we have a skip interval. So here we're using a skip interval as we go through the neighborhood. And we use our sample size calculation to determine that sample size so that we haven't gotten too big a sample so that we're wasting money, and it's not too small of a sample so that it doesn't represent the population of interest. So we have done our calculation, we've figured out the amount, and so now we are basically giving the instructions. So here we are going to every third dwelling. If you go all the way around a block and return to the starting point, then find a new starting point to repeat the process. If there are no dwellings on the street or road opposite to the starting address, circle the block and opposite starting address. So it's the instructions for how to actually implement this once you know that you are doing systematic sampling, so you're doing every third, once you know that you are going to be doing face-to-face interviews, once you know that you're going to talk to 190 people. Then you actually have to do it. So the last piece is always going to be this operational sampling plan, which is how to take all these decisions you've made about your sampling process and turn it into action. How is it actually going to be implemented? So you want to make sure you write that up, especially so that you have your many different researchers or whoever you're hiring to collect this data to follow the same process. Because remember, you want to reduce our non-response bias. We want to not implement bias into the data by skipping the shady houses, for example. So we want to make sure everyone's following the same protocols.